Well, hello and welcome again to our journey through number theory, and we're up to having a look at this sum. This is the sum of the reciprocals of the primes, all the primes up to some number x. So this is a finite sum at the moment, and we're going to prove that this sum in fact diverges as x goes to infinity. That is, if we take the sum of the reciprocals of the primes, that sum gets as large as we please, the more primes we take. Secondly, we're going to do that and also going to obtain some sort of good estimation of how fast this thing grows. Roughly how big is this for large values of x. So the first thing to do is we're going to prove that the sum of the reciprocals of the primes diverges. Now there are lots and lots of different proofs of this. You'll find them in different books. The proof I'm giving here is slightly longer than some others. But the reason I do this is that it contains a number of ideas which will be used again later. In particular, we're going to generalize some of the techniques in this proof when we come to the proof of Dirichlet's theorem. And so although this is not the slickest or the shortest proof of this fact, it is, for our purposes, perhaps the most useful one. So the proof goes something like this. That's what we're trying to prove, that the sum 1 over p prime diverges. Now we begin by looking at the zeta function, which we've seen before. So this is the sum k equals 1 to infinity, 1 over k to the s, and this converges, well behaved for s bigger than 1. And as s goes to 1 from above, then because sigma 1 over k diverges, zeta of s goes to infinity as s goes to 1 from above. Now we go back and use the Euler product, which, as I said, is one of the keystones of analytic number theory. So zeta of s, remember, can be written as this product over the primes, 1 minus 1 over p to the s, all to the minus 1. That was our Euler product. So I'm going to take the log of both sides of this. So I get the log of zeta of s, and I can pull the power down the front, and then the log turns the product into a sum of the logarithms. Now there's no problem with convergence here, because if s is bigger than 1, then both of these are finite, and so I can take the log of both sides and I can expand it out, and so this is all perfectly valid. Now just recall the Maclaurin series, or if you will the Taylor series, for log of 1 minus x, or minus log of 1 minus x. It has a Taylor series of that, which is valid for mod x less than 1. So this you will know from calculus courses. That's the Taylor expansion, or the Maclaurin expansion of this. And I'm going to apply that in here. So now I'm replacing x with 1 over p to the s. I get a couple of minuses to cancel, so I get log of zeta of s then now becomes the sum over the primes, and then I replace the log of 1 minus 1 over p to the s by this sum, replacing x with p to the s. Now the key step now, which is the same we'll see later when we get to Dirichlet's theorem, is to peel off one of the sums, to put n equals 1 into here and take that separately. You'll see why in a minute. So I'm going to now take the sum over the primes of, put n equals 1 into here, you just get 1 over p to the s, and that's the rest of the sum. And now you continue on, add the rest of the sum back in. That's sum n equals 2 to infinity of this. Now the name of the game now is to show that this quantity here is very small, it's bounded. In fact, it's quite tiny. This is the sum for the over the primes, n equals 2 to infinity of this, and I'm going to call this expression capital T. So we're going to show that this then is very small, and that takes a little bit of work. And then to finish off the argument, what we're then going to do is we're going to let s go to 1, And then because zeta of s diverges as s goes to 1 from above, so does the logarithm. So that is, as s goes to 1 from above, that's going off to infinity. That is bounded, this is some finite number, and that will force this one, as s goes to 1, to go off to infinity, i.e. that'll show that the sum of the reciprocals of the primes diverges. Okay, so the only technical thing we have to do now is to show that this sum here is small. And so that's our next task. So I give that a name, I'm going to call that capital T, there it is. And I'm going to start trying to get some bounding approximations for this. First thing, I'm going to toss away the n. I'm going to say that this is 1 over p to the ns times n, and that's going to be less than just sigma 1 over p to the ns. Now, the point about doing that is this is a sum over n now, and if you write this out, you'll see it's just a geometric series, and so you can sum it. It's a, which is the first term, over 1 minus the common ratio. So I can sum this geometric series, and I still got sum over p of this. Simplify that a little bit to get to here, and I'm going to factor out a p to the s. Now, I can, because p to the s is bigger than p, then I can get rid of the s and say this is less than the sum over the primes of 1 over p times 1 over p minus 1. Now this is the sum over just the primes, but this again is going to be less than the sum over the same shape but all the numbers. So I'm adding in extra terms, so this will be less than this sum. Now the point about this sum is that it's a telescoping series, so you can use partial fractions to get that, and then this is a telescoping series, which is you just plug the numbers in and you see almost everything cancels and you just get 1. So this is a telescoping series. So that means for s bigger than 1, this t is less than 1. It's not very big, it's some positive number, but it's less than 1. And so, as I mentioned before, looking back over here, as s goes to 1 from above, the log of zeta of s goes to infinity, log of it goes to infinity, that is bounded, so that must go to infinity, that must diverge as s goes to 1 from above. And that's what I've written over here. So as s goes to 1 from above, zeta s goes to infinity tells me that this sum here diverges. By the way, we also have the interesting fact that sigma of 1 over p to the s converges if s is bigger than 1. So the sum of the power of the reciprocals of the powers of the prime for any power bigger than 1, this actually converges. You can see that from here again, because if s is bigger than 1, this sum is finite. So the zeta of s is finite, log of zeta of s is finite, this is bounded, this is a finite number, and so this must be a finite number as well, provided s is bigger than 1. So there is a nice little proof of the fact that the reciprocals of the primes diverges. Now, although the series diverges, it does so very, very slowly. As I mentioned, the sum of sigma 1 over p for known primes is quite small, even though the sum itself diverges. So we'd like to get some idea of the rate of growth. What's the order of magnitude of this quantity? So the following result is going to give a lower bound on sigma 1 over p, but in fact from it one can obtain the true order of magnitude of this sum, and we show its log of x. But we'll come back to that in a much later chapter, in fact, when we have some more machinery at our disposal. So as usual, when I write p less or equal to x, it's assumed that p is always prime. Now, in order to prove this result, we need a couple of little results which I put in the form of a lemma. The first one says that if for x bigger or equal to 1, the sum of 1 over n less or equal to x, is bigger or equal to log x. Now the proof of that I leave you to do as an exercise. It's not very hard, in fact. I suggest you just draw a picture of the function y equals 1 over x, and then draw up some rectangles and compare the areas of the rectangles with the area under the curve, and you'll find this falls out. So I leave that as a little exercise. And 1 plus 1 over x is less or equal to e to the 1 over x. This follows easily from the Taylor expansion of this. So if you look at the Taylor expansion of, say, e to the z, you'll get e to the z is bigger or equal to 1 plus z, and then you just replace the z with 1 on x. So that follows immediately, really, from the series expansion. So here is our theorem that gives us this bound, gives us this lower bound. It says that the sum of the reciprocals of the primes up to some point x is bigger or equal to log of x minus something. This is just a number. This is the log of zeta of 2. Zeta of 2 is pi squared on 6, so this is just the log of pi squared on 6. In fact, the true order of magnitude, as I mentioned, is in fact just log x. Now, log x gets big very slowly. It does, of course, go off to infinity. So, by the way, this gives us another proof, if one was needed, that this thing diverges, because as x goes to infinity, this goes to infinity and this is bigger than it. And it also, of course, gives us yet another proof of the infinitude of primes. Now, again, there are a number of different proofs of this. There are quite a few you'll see in the books. I've chosen one which I think is the nicest, the most attractive proof. And I think from memory I got this out of Jamison's book on the prime number theorem, which is a beautiful, beautiful book I highly recommend. And I think from memory I got this proof out of that book. So the proof goes simply like this. And again, it's slightly technical proof, as many of these are. So that's what we're trying to prove, that sigma 1 over p is bigger or equal to log x minus log of zeta of 2. Now, we're going to do this by looking at square free numbers. And so by unique factorisation, we can take any integer n and we can write it as a square factor, take out any square factor it's got. It might not have any, n might be 1, but take out any square factor you've got, and you're left with a q which is square free. It's got no square factors. So we let capital F of x be the set of all square free integers less or equal to x. All the integers will have no square factors. Now we're going to consider the sum n, not necessarily p, but just n less or equal to x 1 over n. And I can replace then, using this factorisation, I can replace the n with qm squared less or equal to x. And I can split this sum by saying this is less or equal to, I take the sum over the squares and then multiply by the sum 1 over q of the square free numbers. Now that won't be equal to it, but it'll be less or equal to this one. Now this one here, if you think of allowing x to become very large, then this will become zeta of 2. So this one is going to, this sum here, this finite sum, is going to be less than the infinite sum, which converges to zeta of 2, which of course is pi squared on 6, and we're left with this term here. So, putting all that together for the moment, we have just established then that sigma 1 over n, n less or equal to x, is less or equal to zeta of 2 times the sum of the reciprocals of the square free numbers less or equal to x. So let's hold that thought, and we'll come back to that in a moment. Okay, now looking, of course, we're often thinking about these Euler product type products. So I'm going to look at this is a finite product, the product of p less or equal to x, just 1 plus 1 over p this time. So you write this is going to equal 1 plus a half times 1 plus a third times 1 plus a fifth plus 1 plus a seventh, 1 plus an 11th, and so on of the primes. And again, you take a deep breath and expand it out. You're going to take 1 from each bracket, you get 1. You take a half times 1 from each bracket, you get a half. Then you get a third, you'll get a fifth. You'll get a sixth by taking the product of these two. You'll get a seventh. You will not get an eighth. You'll not get a fourth, by the way, and you will not get an eighth, and you'll not get a ninth. You will get a 10th, an 11th, no 12, 13, and so on. And you can see, if you think about it, this is just going to give you square free numbers. So this is going to be bigger or equal to, because you'll get more terms, bigger or equal to the sum of 1 over q, where q are the square free numbers less or equal to x. So this Euler product gives you square free denominators. Now by lemma 2, we have 1 plus 1 over p is less or equal to e to the 1 over p. So we can take the logarithm of this product we've just been playing with. Log turns products into sums. So this now just becomes equal to the sum p less or equal to x log of this quantity in here. And you can see from here, if you take the log of this, that's going to be less or equal to the log of this, which is just 1 over p. And so this sum is less or equal to the sum of 1 over p less or equal to x. So putting that all together, I get sigma 1 over p is bigger or equal to log of 1 over q, where q is in the square free integers. So I'll just keep that result there for the moment. So we have sigma 1 over p is bigger or equal to the log of 1 over q, where q is a square free integer. Now I want to compare that with the result we had over here. We had over here a formula for the sum of 1 over q of the square free integers. So I can plug this inequality into here, and that means then I can say that sigma 1 over p is bigger or equal to the log of this, and this is just going to be the log of this term divided by that one. So that's going to give me the log of 1 over zeta of 2, sigma n less or equal to x 1 over n. Okay, finally then I can, this is a log of a product, so I can just break this up using the log laws. And finally then I'm going to use the fact that we saw that sigma 1 over n was bigger equal to, for n less or equal to x, was bigger equal to log x. So there I've used the lemma part 1 at that point to replace this sum with log x, and so this is bigger or equal to log x minus this one, and that's the result we wanted to get. So for example, just to see what the numbers look like in terms of sizes, if you take the sum of the reciprocals of the primes less than 10 to the 6th, then you end up with roughly, on a computer, you get about 2.887. You see, it's not very big. It goes to infinity, but because of the log term, it goes there very slowly. On the other hand, if you compare that with the log of 10 to the 6 minus log of zeta of 2, you get about 2.13. And so you see that is bigger than that, and then roughly in the same ballpark. By the way, and we'll come back to this again in a later chapter, if we look at sigma 1 over p less or equal to n, so we stop at some finite value n, and we subtract off log of n, and we then take a limit of that as n goes to infinity, then we will show much later that that limit exists, so I'm going to call it capital M, and it's approximately 0.261497 ... and this is called the Michel-Mertens constant, and we will have a look at that a little bit later in a later chapter. So we'll finish that at that point.